What I'd like to do in this video is discuss solving polynomial inequalities. All right. Now, you've probably solved simple inequalities in the past. For example, if I asked you for the values of x that satisfy this inequality, you could solve it pretty similar to how you solve equations. So this one, it would be all values of x less than 6. All right. So that's all well and good, but what if you had a more complicated polynomial like a quartic, a quintic, a quadratic, a cubic? Okay, you can't really isolate x, can you, in that situation when you have exponents floating around? So, and those are easily solved by graphing. If I was to, let's say I had some complicated polynomial, and let's say that I graphed it, and I want to know where, let's say that for what values of x is it less than 4. So here's the polynomial, here's 4, okay? And so where is this polynomial less than 4? Well, so you can see there the 4, so it's less than 4 for all values less than this blue line, right? So the part of the domain where the function values are less than 4 are going to be everything between these green dots. Okay, that's the range of x values that will have the function value less than 4, but then there's also another one between, let's make it this time orange dots. Okay, so between the orange dots and the green dots, those are the parts of the domain that would be the solution to, let's say, complicated polynomial of x is less than or equal to 4. Okay, so graphing is a great way to solve inequalities. Now, there's a special case where you can solve a polynomial inequality without graphing. Okay? That's going to be where you are able to factor the polynomial. All right? If you're able to factor it, we can take advantage of the properties of factoring in order to solve it without a graph. Okay, so let me talk about that. So for example, suppose we wanted to solve x minus 1, x plus 2, x minus 3 is less than 0. Okay, let me repeat that. If you can graph this function, that would be the easiest way to solve polynomial inequality. Okay, this is a cubic, and I'm not going to discuss how you factor a complicated polynomial. We're just going to start from, we're going to assume that you've already factored it. Okay, if you factored it, if you're staring at an inequality like this, how do you solve it without graphing? All right, here's the reasoning that I would use. So this cubic is going to have some graph, okay, and we know already where it's going to cross the x-axis. We know what the zeros are. The zeros are x equal 1, minus 2, and 3. Okay, so let's put those on our little picture. And so it's going to cross the x-axis at 1, minus 2, and 3. All right. Now, if it only crosses the x-axis at those points, notice that between the 2 points, the sign can't change. Okay, let me repeat that. So f of x between orange dots, between those x-intercepts, cannot change sign, because why? In order for the function to change sign, it would have to cross the x-axis again, right? And we just said that it only crosses the x-axis at those orange dots. All right, so that means that in this region, it has the same sign, whatever that sign is, and over here it has the same sign. over here it has everything that's every side of the x-intercept has some sign that stays constant, because the function again can only change sign at those orange dots. All right. Well, so how do you find what that sign is? Well, okay, that's where you can simply evaluate the function. You only need one value in between to know what the sign of that entire interval is. So for example, the interval that includes x equal to 0, okay, let's plug in x equal to 0 into our function and see what we get. We get minus 1 times 2 times minus 3, which gives 6. Okay, so therefore we know that in this region it's positive. Okay? Now, because there's no exponents, we know that as it crosses the x-intercept, or we know that it's going to cross the x-intercept, it's not going to have a bounce, it's not going to have a little mini parabola close to the x-intercept, because if it did, we'd have an exponent of 2 or 4 or 6, right? So therefore, we already know that it has to be minus in these regions and plus in this region. Okay, let's pretend you weren't clever enough to figure that out. Let me plug in x equal to 2, and you'll see that I get a negative value. All right. So if I plug in x equal to 2, then into the factored form I get 2 minus 1 for the first part. That gives 1. 2 plus 2, so the middle term's 4. 2 minus 3 minus 1, which is minus 4. So it agrees with what we were just talking about. And then you could plug in minus 3, x equaled minus 3, and that would give minus 3 minus 1, minus 1, minus 6. So minus 4 times 6, minus 24. That's also negative, like we predicted. All right. Now, any value bigger than 3 will give supposedly will give a positive value. Now, clearly, let's say x was 1 billion, okay, or 1,000. Okay, some big number. If I subtract 1, that piece is still going to be positive. If I add 2, it's going to be positive. If I subtract 3, it's going to be positive. So I'm going to have 3 positive numbers. So clearly, for x bigger than 3, the function is positive. All right. Now, once you've done that, you've solved this. Why? Okay, think back to our original goal. We wanted to find the subset of the domain of this function where the function was less than 0. Okay? Well, look at our sketch there with the blue plus and minus signs, and can you see that the inequality is satisfied? The function is less than 0 for x is less than minus 2 or between 1 and 3. Right? That's the algebra, the inequality way to express those two regions where we had the function is negative. All right? And so to repeat, they're all going to be the same way. You factor it, you label the zeros on a graph, and then you find the sign in each piece of the xy plane. You find the sign of the function, knowing that the function can't change sign unless it crosses an x-intercept.